Okay, do you see the screen now?
Yes.
Okay, so you know, this TTL standard circuit is shown here. You know, we analyze the input stage, and then we analyzed the last stage, and then we have seen the splitter stage. So we know the operation. So this was for the inverter. We can make NAND gate out of this very easily and simply, or NOR gate. I guess NOR gate is a little bit more complicated, and then it is given here. So, you know, if you connect these parallel stages for the input, then we can obtain this NOR gate. So we can go through the circuits and then you know, understand why this is a NOR gate, and this is you know, something actually easy to analyze. So if you remember the NOR gate, if there's A and B as the input, 0 0 0 1 1 0 1 1, you know, logic wise, or low high, you know that. For the OR, it's going to be 0 1 1 1. This is OR. And if you think about the NOR, it's going to be 1 0 0 0. Okay, so therefore both inputs low will give us a high. All inputs low give us a high. Any input high will give us low as the output. So that's the NOR gate in, you know, in the operation. So you know, one means high, this is low, 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 right? So let's look at what happens here for different cases. So you know, analyzing everything at once here will be difficult. I'll try to maybe do coloring here so that, you know, maybe you can differentiate. So if let's check the first case. If this one is 0 and this one is 0, 0 means 0 volt. I mean, here it's logic 0, here it is 0 volt, okay, or 0.2 volt. If this is 0, what is the state of this QI1? You need to help me with this. Okay? I'm not going to continue without your help. What is the state of QI1?
Saturation.
Sat.
Good. It's going to be sat. So what about this one?
It's also sat.
Also sat. Okay, so we should solve this together. Okay, so if it is sat, then this is 0.2 volts, right? Because this will be 0.2 volt, and then this will be 0.2 volt. So if this is 0.2 volt, what is the QS1?
Cutoff.
State of off, yes. And then what about QS2? This is 0.2.
Off.
That's also off. Okay, good. Okay, so off, off. So this one is off, and this one is off. No current is coming. So what about the state of QO?
Off.
This is also off. Okay. Then this one is edge of conduction, edge of conduction. So the voltage is going to be how much? There will be 0 volt, about around 0 volt here. So this is going to be
BCC minus
Oh,
0.7 minus.
3.6. Okay. So basically we applied low here and low here. Output was 3.6 volts. So it was high. Okay. So the state of the transistors, either we can write it here, maybe how many? 1, 2, 3, 4, 5, 6, 7. Oh, we cannot fit 7 things here. But you know, I guess I'm just doing this with colors, so you will understand that maybe from the colors. Okay, so let's go to the next case. The next case is, let's say we select this color. This color, okay? Or let's select something contrast here. So one of them is going to be low. This one is going to be high. Okay. So that means here for A, we apply again 0 volts, but for B, we apply 5 volts. Okay. So if we apply 5 volts, what is the state of QI2? This junction is on.
Reverse active. Reverse active.
Yes, reverse active. Okay, so this one will be still SAT. Okay, so since this is still SAT, this will be still off. But this one is reverse active. So what is the state of QS2? Okay.
Robot active. Yoksa.
SAT. So if this one is SAT, then this gives a lot of current here. No current is coming from here. This is 0 current, but a lot of current is coming from here. Therefore, this becomes SAT. So if this becomes SAT, then this voltage is 0.8 volts. And then due to this SAT, this will be 0.2 volt. Due to that voltage, this will be 1 volt. And then due to that, this will be off, and this will be off. Therefore, output will be, this is SAT, output will be, come on,
0.2.
0.2, yes, in Turkish. 0.2. In English. That's okay. It's okay. As long as you give answer, I accept. So this is 0.2 volt, which is low. Okay, so is it consistent? High, low. High, low. Okay. So next, we look at the other case. Here is high. This one is low. So this one, therefore, when this is high, 5 volts, then this will be reverse active. I'm filling this quickly. Now this one is going to be SAT. And then this will be also SAT. But this one is going to be 0 volt. So if this is 0, this is going to be SAT. And then therefore this will be also off. Okay, so the colors are helping us. And in this case, this will be also off, and this will be also off. So again, we have SAT here, therefore output is going to be 0.2 volts. Okay. So let's look at the last case, high case. For high case, then this will be 5 volts. This will be reverse active. And then if that is reverse active, this will be in SAT. This is 5 volt. And this is going to be reverse active. And then this will be due to that SAT. And then what? If this is SAT, this will be also SAT. And then this will be also off and off. Why? Because this node will be also 1 volt. Okay. So in the green also, this will be 1 volt. Okay. So in the other case, let's put this one also. Here that would be 5 volts for the white. I mean, for the other case. So therefore, here output is going to be again 0.2 volt. Okay, so therefore we obtain a NOR gate. Is that okay?
Hocam bir şey sorabilir miyim?
Sure.
Input'ta high için 5 volt tercih ediyoruz ama output'ta 3.6 volt elde ediyoruz. Bunun özel bir nedeni var mı 5 voltu kullanmamızın şu anda?
No, not really. I mean, I could say here 3.6 volt because that will be also high. I mean, if you think about the voltage transfer function, it was coming like this, right? And it was coming like this, and then going, oops, coming like this, and then going like this. So this was 0.5, this was 1.2, and this was 1.4. So 3.6 here would be accepted as high, right? So this is 3.6 volts. Is that okay?
Evet hocam, teşekkür ederim.
Okay, so you know, for convenience and for simplicity, I said 5 volt. I mean, you can verify that this is in reverse active even for that case, because for 3.6 volts, I mean, here, this junction, you can check, you know, that's not going to be in saturation or on this junction, this voltage. So for that case, you know, this is going to be 0.8, this is going to be 1.6, and then it's going to be 2.3. So when this is 2.3, this is 1.6, 3 points. Then this is 3.6 is also okay to keep this off. So the junction is here off. Okay, that diode. So it is reverse active. Okay. Any other question? Okay, so we will be doing NAND later on. So there is one more concept maybe we should start introducing you. And in the concept is the switching time. You know, typically we have, you know, load, capacitive load coming from the next stages. So the next stage, when we model the next stage, there is going to be an input resistance, maybe in the next stage. There will be a resistance and there will be also capacitance effectively. So if the resistance is infinity, then even that case, there's going to be capacitance. So this capacitance comes from maybe next stage or from the lines, the output, because it's taken from somewhere and then carried to some other place. So in this line, there might be also some capacitance. So so ideally, when we want to operate this, for the ideal case, when the input switches from high to low, we want, here output to be low and then immediately switch to high. And then immediately switch to low. Okay, so this is what we think, output should be. So that's going to be V in, this is going to be V out. So for this case, it's going to be VCC, for example. Okay. So, however, this does not occur so fast. And normally, let's say your voltage here was high and then goes low. High, and then it goes, let's say, to low to blue. Okay. So when this goes to blue, what happens? When this initially high, this was reverse active, and this was SAT, and the output voltage was 0.2 volt. So this would be ideally 0.2 volt, right? So, however, that 0.2 volt, what happens if I switch? Now, if I switch the transistor or the voltage to low voltage, let's say 0 volt or 0.2 volt, doesn't matter, then this transistor QI becomes what? Right? Becomes SAT. When this becomes SAT, this is now 0 volt. That's SAT. So this one is 0.2 volt. Therefore, this becomes off. Okay, and then thanks to this QI, the base charges are removed very fast. So it turns off very fast. QN turns off very fast. Okay, QN turns off very fast. Thanks to QI that removes the base charges of QN transistor. Okay, so it becomes off very quickly. But when this becomes off, then there will be a current flow through CL, and at steady state, the CL will be charged up to what? This is now off. What is the initial voltage? Initial voltage is 0.2. What happens? It just charges. What is the highest voltage it reaches?
Output high voltage.
Yes, 5 voltage. 5 volt or output high voltage. You're right. So therefore, this is not like the ideal case. Okay, so this time constant tau will be equal to RC times CL. And then we say that maybe at 3 tau it reaches to 5 volt. 3 tau or so. Or we can calculate like 90%, like when it reaches to 90%, we can also find that value. So that's called the delay. Okay, so due to CL a delay occur. Okay, or occurs. Delay occurs, and then CL charges through RC. Okay, with a time constant tau. Okay, so
Hocam,
we can, yes.
high durumdan low duruma düştüğünde V out tekrardan bir delay oluyor mu peki? CL için.
Of course. You know, then the QN initially, I mean, we will analyze that part maybe later on. Shall I talk about it right now, or maybe I should talk about it later on? But the CL will discharge through QN. You know, we'll see that. Okay. Let's solve this one first. But you know, of course, this is going to be like this, but this will be very, very fast, much faster. Maybe I should select a different color for that, you know, not to confuse you. Don't I have any other color? So maybe I should do this. Okay, we'll talk about this. This is the point here. Okay. So now we can do the timing analysis here and find you know, the time for this charging, like how long it takes up to that value. Output switches from low to high. Output switches from low to high. So input switches high to low. Okay, so this is this case. I mean, output switches from low to high. Here, if we say that inputs, I mean, I just did this, but the inputs, let's say the color. So let's select the color correctly. So this one was the input. Okay, input. And then input switches to low to 0.2. Okay, then it goes to, let's say, blue here. And then it will go to red here. Okay, so this is Vn. In the time scale, this is time scale. So the output is going to be first switches, let's say this one. It used to be 0.2. And then this will be increasing like this with a tau. Okay, so let's say this is t is equal to 0. So, and then let's make the color like this, blue maybe, just to be consistent, okay? So here, we know the trajectory here, you know, like how this thing is changing. Sorry, maybe I shouldn't have done this. So we say that this is, you know, operating with tau, and then the equivalent circuit is like this. So transistor becomes off, and then here CL VCC and RC, and this is V out. Okay, and then the V out at this is the time t is equal to 0 plus. So if this is 0, this is 0 plus. Okay, so sorry, maybe not there. T0 plus is here, and that's what happens. Starts from 0.2, and you know that you know, transistor stages. I already mentioned about it here. So you know, Qi becomes SAT, and then Qn becomes off. Okay, so you know, if you look at the time analysis for this one, V out will be equal to, in that period here, you know, in that increased time, what was the equation for this? Final value, remember, V final value minus V final minus V initial. Was it like this? E to the power minus t divided by tau. Was it this way?
Yeah,
Or-
yes, I think so.
Or was this plus? No, this was the case, yeah.
Yes, I
Capacity.
think it's true.
It's correct, right? So what is the final value?
5 volt VCC.
Yes. Minus V final is VCC. V initial,
0.2.
e to the power minus t divided by tau. Okay. So then we can do this analysis and then find, for example, the time you know, where this reaches to steady state to all the way 5 volt, or we can even find, for example, here the time where this reaches to 90%, like 90% time can be determined. So typically for these calculations, this 0.2 can be ignored because it's not big next to VCC. So therefore, you know, we can have a nice analysis here, and anytime in this voltage scale, we can determine what happens to this voltage. So for the 90% time, we can determine, or we can say that it takes 3 tau. At 3 tau, output, V out, reaches to VCC. Does it make sense?
Yes.
You know, V out at infinity, it's going to VCC. So V out 0 plus, it's going to be 0.2. So, you know, in the last year's exams, we ask you, like, you know, determine the timing so that, you know, the maximum frequency of operation is determined. So you might want to define this one value, t, and then you can consider this as t divided by 2. And another, if it is 50% cycle, duty cycle, this should be t divided by 2. So therefore, you can find out the frequency of operation, maximum frequency of operation 1 over t. Okay, so if these delays basically determine your switching speed, right? If the delay is high, then this cannot switch very fast. Therefore, your computer or your microprocessor cannot operate fast. Is that clear?
Yes, it is.
Okay. So this one was the easy case because, you know, QN was off. So this was off, this was sat. So therefore there was only charging through here. And it was simple RC charging equation. So this other case is a little bit more, how would I say, complicated. For this other case, I'm going to select the red color. Okay. So when the signal goes into high, that's the case. Okay. So it used to be low, it goes high. So when this goes high, right now, this is the case, or this is the case. Okay. So remember initially, maybe the blue color was, this transistor was, you know, here for the blue case, this transistor was what? This was sat, right? So this was off. So for the red case, when this is 3.6, or let's just say 5 volt for simplicity. Okay, 5 volt. What is QI? This junction.
Reverse active.
Reverse active.
Yeah, this junction is off, this junction is on. So it is reverse active. Okay, so if it becomes reverse active, what about the state of this transistor? It's pumping a lot of current here.
Sat.
What happens to QN?
Saturation.
Saturation. But you know, there's a capacitor in there. So what is that capacitor voltage initially? CL at T is equal to 0 plus. Sorry. T is equal to 0 minus. What is VCL?
VCC.
5 volts.
5 volt VCC, yes. Okay. What about VCL 0 plus? So let's say this is 0. T is equal to 0. Can the capacitance voltage change immediately?
No. No.
So this will be also VCC, right? Okay. So maybe I should go to this color. VCL 0 plus is also VCC. Okay. So therefore this voltage is going to be VCC. You say it's saturated. When collector emitter voltage is 5 volt, QN cannot be saturated. What is happening?
Ya forward aktifliğe mi giriyor bir süre?
Yes. Yes, correct. Perfect. So since at T is 0 plus, we collect the emitter is 5 volts because that's also equal to this one value. Okay. Qn will be in forward active so it will discharge Cl down to what? 0.2. Then the state of the Qn turns to Sat as we expect. So that will take some time. Is that clear?
Yes.
Yes.
Okay. Okay, so we can calculate that timing, like how long it takes, but we need to use the forward active initially, forward active model of the transistor Qn. So for Qn, I guess maybe I can draw somewhere around here the circuit. So the model for that discharging, the model is going to be like this. That's going to be forward active, right? So forward active means this is going to be beta F times what? I base, okay? So we need to calculate this I base here. In the I base, in the model, this is going to be 0.7 volts. And then what else? We have this other transistor here. And for the other transistor, we need to draw the model. And then in the model of the other transistor, this will be, let's see, I don't want to make a mistake here. This is VCC. I guess this will be the case. And then there's going to be current here. And this is going to be beta R times I base of I. And I base of I is this one, I base of I. And that's going to be VCC. And this will be also 0.7 volts. So this will be 0.7 volts here. And this will be 0.7 volts. So this I base of N is going to be, let's say, I base of N, and that's going to be this current, I base of N. Okay. So the current discharging that is going to be a linear current. So I base of N will be equal to beta R plus 1 times I base of I. What about I base of I? It's going to be beta R plus 1 times I base of I is equal to 5 volt minus 0.7 volt minus 0.7 volt divided by RB. Okay, so we can find this current, and if I multiply this current by beta forward, it's going to be this current, okay? So IC of N is going to be beta forward plus 1 times IB of N. So I can model this. So this is the current. So I can say that my discharging is going to be like this, with a constant current source, IC of N, and then a capacitor. Now this is my circuit model. Is that clear? Okay, so this is the fixed current, constant current, beta F I base N, which I call it ICN. So, you know, this is going to be the model. Until V out reaches down to 0.2 volt. Then the transistor model will switch and change. So now the tricky thing is this. So if I can find the time, so this will be the time. So, you know, this current will be almost a lot of current for discharging. So until here, it will be coming like that, but I know from my circuit experience how that value is, you know, calculated. So one way to assume RC to be infinity, so then it's going to be a linear discharging, or we can find that value maybe exactly. So let me do this here for the output. For the output, you know, initially output is VCC, right? I mean, we talked about it. So so V out starts from VCC, and the trend of this one is like this, and the time constant here is going to be tau. So time constant is tau. So if I can find VC or CL, VCL or V out initially, and VCL at infinity, then that's going to be this value, right? At infinity, when it's fully charged, that's the value. So let's go to maybe, I don't know, this color. So what is this value? V out at infinity. How do we determine that? Hmm?
0.2 volts.
No. That's the point where the state is going to change. At infinity, like think about just this circuit here. Don't think about anything else. This is the circuit. What is this? V out at infinity.
I think it will act as an open circuit since there is only DC.
Yes, so CL will be open circuit. So therefore, V out at infinity is going to be VCC minus RC times ICN. Is that clear?
Yes.
So this is V out infinity. So it's going to be a minus value because ICN is large because it's beta times I base. Okay, so the trajectory is like this. So this is now trying to discharge within this line, and that cannot continue up to this 0.2 volt because the state of the transistor will switch. But until that point where it becomes 0.2 volt, this will be the state. So we can write the equation at that line. So this is V final. So I can write V out of T equation. The final value, V final minus V final minus V initial, e to the power minus T divided by tau. Okay. So at this T is equal to, let's say 2, V out T2 time, the voltage is going to be 0.2. And then, I have all these values here. VF minus V initial, e to the power minus T2 divided by tau. So from here, we can determine T2. So we can obtain, okay, so T2 can be determined. Is that clear?
Yes.
Okay, so this is the most confusing thing actually in this timing analysis. To know that actually it's very simple, but students, always take this thing infinity, CL infinity is not 0.2. Okay, so that's the critical thing. CL infinity is, V out infinity is this value. Okay, VCL infinity is equal to V out infinity. So that's this value. So basically, the discharging occurs very fast here. So the switching time is very short. T2 is very short. Does it make sense? If we had ignored this RC and say that it is infinity, so still, the slope the slope is very fast, almost like linear discharging. And that could be also giving you enough correct value, a good estimate. Okay, but you know, this will be stopping here. So I guess that's it in last year's exam questions. You know, again, there are many examples about this, how to determine that T2. And sometimes for simplicity, we say that take that voltage, not 0.2, but take it as 0. So, you know, equation becomes, you know, instead of the 0.2, we can say, you can just assume it to be 0. Doesn't matter, but, you know, maybe a little bit simplify. Is that okay? So the time between 0 and T1, Qn is forward active. So that should be used for your analysis. And that's how you need to solve.
Hocam T1 neydi ya? T2 değil mi o? Olması gerekmiyor mu?
Sorry. Yes. Sorry. I don't want to confuse. Sorry. T2. You're right. Thank you.
Hocam bir de ben bir şey soracaktım. Orayı tam kaçırdım da. T2 bu şey low'dan high'a geçerkenki süreden daha kısa dediniz. Bunun sebebini söylediniz mi? Orayı tam anlamadım ben.
Here, for the charging, there is passive charging. So the charging is only through RNCL. Whereas during the discharging, there is an active element. Okay. This maybe the active element helps to discharge CL very fast. Is that okay?
Evet hocam anladım. Teşekkür ederim.
That gives a current source of value of this much. You know, very large current in there indeed. Okay, very large current here. So, you know, typically we ask timing questions like the charging and discharging times in the exam. So you need to look at last year's exams. I guess you will be seeing how we ask questions here. Is that okay?
Yes.
Okay, then let's give maybe a 10 minutes break. And then I'm going to maybe solve some questions, you know, from last year, midterm 1 questions. Is that okay?
Tamamdır hocam.
Yes.
Okay, you asked to solve some example questions last time, so I will be doing that. Okay, so I realized that you know, some students copied you know, these exam questions, and the exam questions were given to I don't know, copying room. They are not in the best condition. I mean, the things that we find out. So some of them have already solutions on them. Some of them are just questions. I don't know. I thought, you know, solutions are also here. Uh-oh. No solutions are here. Oh, maybe this is the copy that we uploaded. Therefore, there are no solutions. Oh, this is my handwriting. Okay, so I solved this. There's an example here about an RTL. So what do you want to do? Which circuit do you want me to solve? An RTL or these kind of things? This is interesting.
Hocam ödevin bir sorusuna baktım ben. DTL'di sanırım. DTL çözebiliriz belki. Diğer soruya bakan arkadaş varsa.
No, but I cannot solve the homework question.
Yok homework değil. Buradan DTL sorusu çözebiliriz dedim.
Okay. You know, the structures that we have seen are very common structures, but in the exams, we sometimes ask, you know, different looking structures and circuits. Okay, so, but, you know, first, I guess you need to understand the standard questions and then look at this. For example, when we give you a circuit like this, what is this? Can you identify which type of you know, circuit this is? What is this? DTL, RTL, TTL?
TTL, right?
TTL, right?
Yeah, it is TTL. So look at the input stage. It's very familiar, right? To you. The input stage, input A, input B. Okay, so this is same. And then splitter transistor, right? Splitter transistor. And on top of the splitter transistor, I mean, instead of putting the diode here, it's just moved here. Okay, so little tricks like this we do. So we try to understand, if you understand, you know, the circuit. So this is something very similar to what we did. High, low, low, low. Remember? What was this? NOR gate. I mean, this is exactly, almost exactly, the circuit that we have solved for NOR gate, TTL NOR. The only difference is maybe placement of the transistors, and then this diode is moved here. Okay, so don't be scared if you see a circuit like this. What is this? You know, this is just a DTL. So I wrote down the state of the transistors one by one here, so you can understand what this is. What is the function of this gate? It is a NOR gate. The output is filled, transistor states. Now calculate the fan out, maximum fan out of this gate when output drives similar gates. Uh-oh, we don't see the circuit, so but where is the output? Output is here, right? So V out is driving similar gates. Actually, V out is driving similar gates means it is driving this. Okay, so for each of them, for out input high and input low, you need to calculate I input prime for low case, I input prime for the high case. Okay, for the low case, the current is going this direction. For high case, the current is going in this direction. So, I mean, you need to, I guess we will be solving this kind of, we haven't solved the TTL fan out yet, have we? Did we find the TTL fan out? Yeah, we did. Okay. So, in any case, so let's look at the questions again, like fan out, when output drives similar gates. So we need to look at for the high case and the low case, and then minimum of both of two will be our maximum fan out. So also the power dissipation is asked. If the input is VA and VB are shorted together, that means if the transistor NOR gate, sorry, so this is the NOR gate, right? So it should be like this. So if they are connected together, what is the power dissipation if fan out is 10? Fan out is 10 means there are N is equal to 10. So for the low case, you need to find the power dissipation. And for the high case, you need to find the power dissipation. And then you need to take average of it. So this is just roughly like how the, states are going. So in many cases, you calculate already these currents for one part of the circuit. So if you calculate the currents, for example, for fan out, then you don't need to recalculate them. I mean, if you know the case, and then if you know the currents from those branches for those cases, then you can just use it, okay? So you can save time. So this is my handwriting. This is a simple RTL. The only thing here is that there is this resistance here. So that kind of changes a little bit things. Do you have these questions? You don't probably. We should be distributing you this. Okay, wow, this looks like, again, an interesting question. And what is this?
RTL?
Yes, RTL. But, it has a weird, maybe, topology. So shall we find the cases here? So let's say this is 0. This is 0 volt. What happens to this? What happens to this?
Off.
Okay. So off means this current is?
0.
0. Okay. So now here, this is, what type of transistor this is?
PNP.
PNP. Okay. So the PNP transistor is a little bit confusing for us, but nothing is different actually for PNP. There is this junction and then this junction, okay? Sorry, that junction is reversed. Okay.
Mhm.
So, do we know which junction is on, which junction is off?
First one is on, I think.
No current here.
Oh, nice.
Which one?
One below.
So
BCB.
this should be off, but can this one be on? We don't know. Probably both of them are going to be off. Because there is no way for the current to go in this direction, because this side is connected to VCC. So probably both junctions are off, because this is also reverse biased, right? I mean, current cannot go this direction. Current cannot go this direction. Huh?
Yes.
This is the short, right? So then TO is off. This is TO. So therefore, the current through here is going to be how much? 0.
0.
Therefore, what is VY?
0.
Okay. So input 0, we can write this table here. A, B, and then output Z. 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 0, we obtain 0. Okay?
Mhm.
So if any one of them is high, what happens? Let's change the color and go to blue. And let's say that this one is high, 5 volts. This one is 0 volts. What is the state of TB?
Akım olacak burada. Açık sat.
Yeah, when it's switched, we assume that the currents are enough so that it can put it into saturation.
Hmm.
What about this one?
Off.
Oh, okay. So since this is SAT, this is going to be 0.2 volt, right?
Mhm.
Then the circuit equation or equivalent circuit will be switched to this. So this is 0.2 volt. And then there's this transistor here, and then this one. You know, my gut feelings tells me that then this transistor is going to be on because this junction will be on, So if this junction is on, this transistor T0, because this is emitter, this is base, right? EB on means transistor either is in forward active or in saturation. So my assumption, if the resistance values are corrected, this will be in SAT. So the output is going to be, this will be SAT, so this will be 0.2 volt. Therefore, the output is going to be 5 minus 0.2 volt. So it's going to be 4.8. So it will be high.
Hocam saturation assumption'ı nasıl yaptınız?
Typically for the digital circuits, we like to use the transistor in extreme conditions, right? So remember the regular RTL? I mean, we say this will be the case, right? I mean, here is the regular RTL. So we typically like to switch. If we apply 5 volt here, we want to get 0.2 volt here. Why? Because we want to get this thing set. So we arrange RB and RC so that it will be in SAT. So maybe we need to verify this, okay? But if it is forward active, maybe this will not be 0.2, but this will be maybe 2 volt or 1.5 volt. But we don't like that. I mean, when we apply high here, we like this to be low. Therefore, if this junction is on, we have two options, either forward active or SAT. And my assumption, I mean, without any calculation, is going to be that it will be in SAT. I mean, you can go ahead and then verify it, but for quick, I mean, if somebody asks you, what is the state of this, what is the function of this circuit, that's what you do. For the next case, if this one is 5, this one is 0, it is going to be again 4.8. For the next case, let's say this one is both 5 volt and 5 volt. Again, this is going to be 4.8. So this circuit is what circuit? Is this NOR?
OR.
Yes, it's OR. So this is the circuit, A, B, and Z, or Y. Okay, so sometimes in the exams, we ask you this, and then, here it's verified that it is in saturation. But look, this is found, the same table. So OR gate. And next question is, what is going to be the fan out? For the fan out, again, you need to calculate for output low case and output high case. So necessary inputs are provided to get this one. And we assume one of these next gates are connected here. So a similar next gate is connected. So that's how we find the fan out. And we need to check for the cases to keep this transistor in saturation. Okay, for the output high case, for example. For the output low case also, I guess there won't be any problem for the output low case, because when this is low, the next gate is like this, right? So no current is coming here. So when this is 0 volt, fan out or low is infinity. So you need to only look at the fan out for the other case. Is that clear? I'm just going through this very fast, I mean, so that I can show you a few other questions. I mean, for preparing the exam, don't just limit yourself to the standard circuits that we tell you, we ask you, because, I don't know, for the sake of teaching you completely, we try to check if you understand the subject by showing you some other circuits than standard circuits.
Hocam bir şey sorabilir miyim?
Hı.
Bende var bu sorular ve biraz baktım ben çözümlere falan da. Şimdi bu şekilde devrelerin çözümleri hem uzun sürüyor hem de bazen assumption yaptığımız için hani denemek zorunda kalıyoruz falan. Şeyi merak ediyorum. Sınavda yani nasıl olacak ve işte süremiz yetecek mi, ne olacak? Yani hani sınavın uygulanışını da merak ediyorum birazcık. O konuda bilgi verebilir misiniz acaba?
I mean, these are the questions, okay? So it typically takes the general idea or the trend is, if we give you, okay, let me give you a graph, okay? So this is the class average versus the time we give you. Time and average. Okay. So the time and average typically goes like this. Okay, so if we give you for each question 5 hours, the average will come to mostly, I mean, assuming that you understand the subjects and whatever, it comes to 90. Okay, but we cannot give you 5 hours. For each question, we typically give you maybe half an hour. Okay, so in 2 hours, we ask you 4 questions. So in 30 minutes, the average comes to maybe around 50. Does it make sense?
Yes.
So if you solve a lot of questions before the exam, okay, you will be able to get maybe here in 30 minutes. So this is the average, okay? So then different students do this thing like differently. So in 30 minutes, you get somebody getting hundreds, somebody is getting 90, somebody is getting this and that. So you can determine yourself which one of these students you are. And the time constant of solving the question, I'm explaining very technically, right? And mathematically. So the time constant depends on your familiarity with the with the questions. Okay, so no matter what we do, I mean, if we give you like 1 hour, so it's going to be again like maybe 70 points or so. So, but there will be always complaints about time is not enough, because the subject is not very surprising here. So we don't ask you surprising questions that either you do it, or you don't know, you get 0. So the questions that we ask is questions like every student can do it, if we give enough time. And then but we have to, I mean, check how well you studied for the exam. And then if you studied for the exam, very well, then you will be here. No problem. Is that clear?
Evet hocam.
So now you are not very familiar with the questions and you haven't solved any questions. So therefore, I think now your performance is around here. So in 30 minutes, but if you look at the questions and solve it yourself, and then, first try to solve it yourself. Maybe you will solve it in 1 hour. And then look at the answers. And then, take another question and then solve that one. And then, because it's very trivial. I mean, we ask for the voltage transfer function. What about the fan out for output low case, output high case? And what about, the power dissipation? So that's kind of it. Okay. So the only thing is that sometimes, I mean, we give creative circuits like this, you will not be faced with in the past. There maybe, so you need to maybe spend a couple minutes to understand, the operation in general. What is this? For example, here, if this is low, you know that this junction is going to be on. And when this junction on, it means it is either forward active or SAT. And typically we prefer to make it SAT. So if this is SAT, then the output voltage reaches to 4.8 volts, for example. And then you keep continuing, from that point. So, but this is -5 and 5. So I'm just quickly, giving you a reference. So, I mean, we try to differentiate like how well you understand the subject. And if you understand the subject very well, then for these kind of different questions, you will adapt yourself very fast and you will solve them very fast. Is this the correct question? So this is, now it turns to my handwriting. This is my handwriting. What is this? Oh, maybe this is a different question. This looks like a different question. They mixed. So when you get a question like this, you know this topology, right? So, I mean, once you know this topology, you know that this is quickly 0.5, this is 1.2, this is 1.4 volt, and then the only this is 3.6 volt, and the only difficult thing is this one, and you learned how to solve that, I mean, in the class we have done, and you can solve it. That's it. And then, what are the questions? Find voltage transfer function, breakpoint is important, so find this. Maybe there is an, tricky things like this. We say that if the slope wants to be equal to this slope, what should be the value of one of the materials? So you will find out that, if this slope is equal to this slope, the ratios will be determined. So we output high. Maybe I should change my color here. This is not very good. So I'm quickly showing you, these, how to go through these questions, okay? So we output high minus VOB divided by 1.2 volts minus 0.5 volts should be equal to VOB minus 0.2 volts divided by 1.4 volt minus 1.2 volt. Okay, so this is fixed, so this is 3.6. So from here, you can determine the VOB, okay? So you find the VOB so that this will be only single slope. And then that VOB, how can you obtain that VOB? What value of RC gives you that VOB?
Hocam
Okay.
slope'ların eşit olduğu soruda mı verilmiş?
Uh-huh.
Ha,
The
tamam.
question is here.
Tamam.
So determine new RD and VOB values so that single slope.
Anladım.
Okay. So as you see, we try to be creative because the topology is so same. I mean, so if we ask you the same topology, nothing new is coming, or design, you know, so by doing this, we check if you can design something. So, you know, I guess you need to look at, you know, as much as questions in the last years possible, so that, you know, you can quickly solve these things. Okay, so about half of the time, maybe we ask similar topologies, like this one is the NOR gate. I mean, NOR gate that we have determined in the class also, right? In lecture hours. You know, high, high, low, low, high. Maybe the circuit looked a little bit different than this one, but it is the same circuit. But maybe in one exam, you put this one here, you know, like the diode. So if the diode is here, it should be the same function, nothing changes. So, you know, the point in the exam is to see how, I mean, if you memorized or if you face with some variation in the circuit, can you solve it? Like that's the purpose. I'm giving too much information, maybe this is recorded. So maybe I should delete this, huh? Not share with you this recorded part. Let's see. Okay, look, I mean, this is interesting. I mean, we just put here one resistor. Okay, so what happens? If you can solve this thing, your circuit knowledge, is it good enough? We are trying to differentiate the questions, okay, each year. Oh my God, what is this? We ask very interesting questions. I should look at these last year's questions. (2010). Okay, this is standard. So the thing about here is, you know, we set some noise margins for finding the fan out. Shall we do this one? How to approach the circuit. The time is up, but let me show you here. So noise margin high is 1 volt means if this is driving another gate and similar gate. Okay, so when the voltage here, what is this V out? you need to solve this for this V out value. And this V out value is going to be V input high plus noise margin high. So for this high case here. So V input high is 1.4 volts plus 1 volt. So this is 2.4 volts. So the thing is, we need to put here 2.4 volts and then calculate the current that is coming from here for 2.4 volt. And that value is going to be 2.4 plus 0.7 plus whatever, 0.7. So 3.8. So 3.8 volt will be here. And then from here, you know that for that case, this is off. This is off. So I can find here this current, that current, and I out will be equal to 5 minus 3.8 divided by RC times beta F plus 1, because that's the base current. And then this is the emitter current. Okay, so that's how you find I out current, and I in current for output high case is also very easy to find. We learned from your previous courses, examples. This was 3.2.3, I guess. So I find this current, and then that current times beta R, I in prime, is equal to beta R times I base prime current. And I base prime current is equal to 5 minus 2.3 divided by R base. Okay, so you don't need to literally lose time here if you know and you did enough examples here. Is that okay?
Evet hocam.
Okay, I did this quickly, but okay, so there might be some confusing things like this diode, for example, but there's no function of that diode. That diode is typically put for input protection. Sometimes we put also this kind of diode to input. So they always off normally. Okay, so but if the input is below like 0.7, minus 0.7, then this diode turns on and then protects the burning of this. And if the input goes beyond 5.7, okay, so Vin remains between 5.7 and minus 0.7 due to these diodes, thanks to diodes. And then it creates protection. But it doesn't affect any of our circuit operation. Okay? Is that clear? Okay. I'm stopping here. Time is up.
Teşekkürler hocam.